We are going to talk about another hybridization model, the SP model. And we're going to use that model to explain the molecule of acetylene, so an alkyne. Remember that in the line structure, by the way, we only need to draw this in the line structure because we don't draw the hydrogens attached to hydrogen. But now, how can we explain that now carbon makes only 2 bonds, so each carbon, 1 bond to another carbon, and a bond to a hydrogen. Now for that, we're going to use another hybridization model, as I said here. So in previous videos, we remember that we have, this is the orbital 1s, and we have moved 1 electron from the 2s to the p's, and here I have 2px, 2py, 2pz, and my electrons were here. There's remember carbon is 6, and that is the mass of the most abundant isotope. So here we have my electrons. After promoting 1 electron over there, I have 4. But now, to explain the geometry of acetylene, we're going to need to make 1 sigma bond and 2 pi bonds. So what we're going to use now, the model, is we're going to make a hybrid by mixing 2 atomic orbitals. And we're going to make 2 hybrid orbitals. And because I'm mixing 1 orbital type S and 1 type P, these are called SP. And also, we're going to notice that we have 2 unhybridized p orbitals. So now let's use this to make the drawing of our molecule. So let's do, I need a sigma bond. And now in the SP hybridization model, because we have 2 orbitals, they're going to be placed in a line, so as far away as possible. And now the sigma bond between the 2 carbon is formed by the overlap of, this is a sigma bond, overlap of 1 sp orbital from this carbon and another sp orbital from the other carbon. So that's the nature of the sigma bond here. Also, each carbon has a bond to a hydrogen, and hydrogen is using 1 orbital type 1s. So describing the bond here, that is a sigma bond formed by the overlap of 1 sp orbital from the carbon and 1 orbital 1s from the hydrogen. Same thing here. Now, in each carbon here, we're going to have, say, there's 1 p orbital unhybridized, like that, and they're going to produce the lateral overlap that we talked about before, like that, and this is your pi bond. And that pi bond, again, is the overlap by 2p and another orbital 2p from the other carbon. Yet I have another p orbital here. Notice that we have 2 unhybridized p orbitals. So the other p orbital, let's use another color here, would be perpendicular to this. So I'm going to draw it slightly tilted. And so that's another pi bond. One is going to be here and the other in this plane. Overall, the molecule, notice all the atoms lie in a line. So the geometry of the molecule is linear. Every atom is in this line. For the geometry, remember that we don't take into account what are the electrons in the pi orbitals, in the pi bonds. We know that there's 1 pi bond here, the one in this, and one other perpendicular that I drew in green. Right, one here, but that doesn't matter, doesn't count for the geometry. What counts is where are the atoms, the nuclei, and they are in a line. So this molecule is linear. Okay, so that hybridization model then allows me to explain the geometry of acetylene. And we're going to be talking more about them, other geometries more complex. Oh, I forgot to say something a little bit. So here we're mixing one S and one 2p. So these orbitals that we call sp are out of two orbitals, we have one out of two orbitals that we're mixing is S character. So we say it's 50% S character and 1/2. So I'm mixing one and one. So one out of two p orbital, which is another 50%. So that is p character. Because of that, it's like half and half. The orbitals that we form are much closer to the nuclei than the, let's just say, Spain, kind of the shape. If they are sp2, they will be a little bigger, say, and longer because of more p character involved. Say that this is sp3, which is only 1/4 of S character, and the sp2 is 1 out of 3 is S character. So they're going to be longer. That would be important to explain other properties in the molecule. So that's all for now.